So let's start with part two on the Taylor series and Maclaurin series. So to recap, we use Taylor series as approximations for non-polynomial functions, sometimes such as trig functions are difficult to evaluate it. Besides the regular, for instance, trig on pi over 3, pi over 4, and so on. And so it's easier if we can express these as a polynomial, and we can approximate them in that way. So we ended the last video with cosine of x. We wrote the Maclaurin series. And just to recap, the Maclaurin series is the approximation when a equals 0, and then Taylor series is just for any a that's in the domain. So here we have the Maclaurin series for cosine of x that we ended with last time. And so now we want to do the example where we have f of x equals x times cosine of x. So obviously this is the same as this, except we're multiplying by x. And literally that's all we need to do. We just need to multiply this series by x. So we get x sum from 0 to infinity, negative 1 to the n, x to the 2n over 2n factorial. And now this is essentially a constant as far as this series goes. So we can just bring it inside. And we get the series from 0 to infinity, negative 1 to the n. X to the 2n times x will give us a x to the 2n plus 1 over 2n factorial. Okay, so now let's look at one that's not trig. So we have 3 times 1 minus x to the negative 2. So let's take our derivatives. F prime of x will be 6 times 1 minus x to the negative 3. F double prime of x will be 18 times 1 minus x to the negative 4. F triple prime of x will be 72 times 1 minus x to the negative 5. Now let's evaluate at 0. So f of 0 will be 3. F prime of 0 will be 6. F double prime of 0 will be 18. And f triple prime of 0 will be 72. So now let's write out our terms. 3 times 1 minus x to the negative 2. And just to recall, the terms in the Maclaurin series, we have f of 0 plus f prime of 0 times x plus f prime double prime of 0 over 2 factorial x squared plus f triple prime of 0 over 3 factorial x cubed up to infinity. So we have 3 plus 6x plus 18 x squared over 2 plus 72x cubed over 3 factorial up to infinity. And that's 2 factorial, which is also 2. All right, so let's simplify these fractions. We don't really see a clear pattern here yet. So we have 3 plus 6x plus 9x squared. 72 over 6 would give us 12x cubed. So now I think we see the pattern. 3, 6, 9, 12. So let's factor out a 3, and we get 1 plus x plus 1 plus 2x plus 3x squared plus 4x cubed. Dot, dot, dot. So now let's write this as a sum. N equals 0. And so when n equals 0, the coefficient is 1. When n equals 1, the coefficient is 2. When n equals 2, the coefficient is 3. So the coefficient is n plus 1. X to the what exponent? So we have x to the 0, x to the first, x to the second. So it's going to be x to the n. Then let's look at ln of 1 plus 5x. These are all following the same patterns. It doesn't really matter what the function is, you're going to do the same thing. There is one exception that we're going to look at the end, but mostly you can do this with the last one. It just gets difficult. But for the most part, you can start taking derivatives, plug in 0 or whatever. So in this one, it's going to be a equals -2, but Maclaurin series, it's a equals 0. So we take our derivatives. Take up to 3, but you can take more if you like. Cubed. Then, after you take your derivatives, evaluate it at 0 or whatever number we're given. So f of 0 is 0, f prime of 0 is 5, f double prime of 0 is -25, and f triple prime of 0 is 250. So now we can write out the terms of the sequence, or the terms of the series, I should say. So we get 0 plus 5x minus 25x squared over 2 factorial plus 250x cubed over 3 factorial minus out to infinity. So let's simplify our fractions. We get 25 halves x squared plus 125 thirds x cubed. And so I think we can see kind of what's going on. 5x to the first minus 1/2 5x squared. So this can help too if you have trouble seeing the pattern, or exactly how, maybe you see the pattern, but it's hard to write out what the series is. Maybe write it like this so you can see exactly what is happening from term to term. So n is going to go from 1 to infinity. And we have, so alternating signs. So let's do a -1 to the n plus 1. Now let's check to make sure that's right. When n is 1, this will be -1 squared, which is positive. When n is 2, -1 to the third, which is negative. So this works. And then we have 5x. First term is 1, second term is 2, third term is 3. So this is 5x to the n over n. So we have, I think, 1 over 1, 1 over 2, 1 over 3, and so on. And so there is our series. Okay. I'll stop here. I don't want to do too many examples all at once, and we'll do the last 3. I think there are 3 more in the next video.